Welcome to my channel. In this video, we are going to learn heating effects of electric current. Now let us look at this simple circuit which has a resistance connected to a source of energy, that is a potential difference, which the current which flows is measured through the ammeter. As we know, current is the direction is from positive to negative. So this is the indication of the direction of the current. A battery or a cell or this potential difference is the source of electric energy which generates the potential difference and sets the electrons in motion. Therefore, you have the current I flowing through the circuit. Now, to maintain this current, the source has to spend some energy. Now, where this energy goes? A part of the source energy is in maintaining this current is converted into useful work. So, when this current is flowing through, when this current I is flowing through this circuit, a source energy, that is source energy is from the battery and that is maintaining, and that current is converted into useful work in maintaining that current. So what does that do? Example, let us consider a fan. The source of energy is converting some of the energy into mechanical energy, thereby it is rotating the blades of the fan. And as you know, if you constantly use a fan, then after some time it gets warm up or heated up. Reason being, there will be a rise in the temperature of the fan. That means there is heat energy. There is heat energy. So, energy gets dissipated in the form of heat energy. So, when the total amount of the energy, source energy, is spent and converted into a useful work, it can get dissipated into a heat energy. So, electrical energy transforming into heat energy. So, that is the basic essence of this. For example, when an electric current is passed through a high resistance wire, now this resistance, if the current is passed through this high resistance wire, for example, let us consider a nichrome wire used as the resistance, then it becomes very red hot and produces heat. This is called heating effect of current. Now, you might have seen that certain filament bulbs which become very much red hot. So, essentially what is happening, there is a transformation of energy, electrical energy into heat energy. Let us try to understand what does that mean. Now, we know in mechanics that mechanical energy is used to overcome friction and is converted into heat. Similarly, electrical energy is converted into heat energy when an electric current flows through a resistance wire. So, let us write the definition first. Electrical energy is converted into heat energy when an electric current flows through a resistance or resistance wire. So, this is the definition. So, basically when you look at and compare the friction in mechanical energy, the role of resistance in electric circuit is similar to friction in mechanics and resistance in electric circuits are similar in their role. So, resistance in electric circuits is similar to friction in mechanics. So, the roles of both of them are same. Now, let us try to derive that heat energy which is dissipated. So, when an electric current I is flowing through a resistance wire, let us find out what is the heat produced. Now, we have seen that I is flowing through R. The current is I flowing through the resistance R. And let V be the potential difference and T be the time during which the charge flows. The charge Q flows, during which the charge Q flows. Therefore, the work done in moving the charge Q through this potential difference V is work done. We know that work done is VQ. Why? Since V, the potential difference, is which I have discussed in my previous videos. Therefore, the source must supply energy. So, source must supply energy VQ in time t. Hence, the power input to the circuit, by the source can be power P, I will write capital P, is energy by time, right. So, energy is here VQ. So, VQ by T. Now, this I can write it as V into I. Why? Since Q by T is nothing but current I. Therefore, the energy supplied to the circuit E is power into T or P into T, or I can write, using this equation, I can write P as V into I into T. This is E. Therefore, energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H, I can write it as produced in time T. I can write it as, so I will write this as work done is consumed into heat. So, this energy is converted into heat, therefore, I will write H. So, H is equal to VIT, or I can write H is equal to I square RT. Why? We know that V is equal to IR from Ohm's law. So, when I substitute here, so I have IR into IT. So, that is I square RT. So, H is equal to I square RT. So, this is the formula, and this is known as Joule's law of heating. This is known as Joule's law of heating. Here you can see 1 joule of heat produced, 1 joule of heat produced when a current 1 ampere flows through a resistance. How much will be the resistance? Of 1 ohm in 1 second. In 1 second. So this is important expression which we will use it in numericals. Now this heat produced is now directly proportional to 3 parameters. Number 1, it is directly proportional to I square for a given resistor, and then it is directly proportional to resistor R for a given current. So it is proportional to I square, it is proportional to R, and it is also proportional to T, for which the current flows through the resistor. T is time T. So this is directly, which means what? Which means as the current increases, suppose you increase the current double, then heat produced also gets doubled. Heat produced increases. As the resistance is increased, heat produced also will increase. As the time during which the current passes through is increased, heat produced also will increase. More heat per unit time if resistors are connected in series. Why? Because in series connection the equivalent resistance increases. So if R increases, heat produced increases. If the resistors are connected in parallel, then the effective resistance or equivalent resistance decreases, therefore heat decreases. Now let us see some points that will be important to remember. Not all appliances convert all energy to heat energy. What does that mean? Example, let us consider fan. Now most of the energy is utilized in running the fan. That means it is converted into mechanical energy. In the beginning itself, I just gave this here. Rotating the blades of the fan, that means running the fan. So most of the energy is converted into mechanical energy, and only a part, very small part, is converted into heat. So fan becomes slightly warm up. So you will not have fan becoming very much heated up, and that we don't want. So only part of it. So the one important point here is what? Not all appliances convert all energy to heat energy. Example is, as I mentioned, fan. Now most of the energy gets converted into heat energy in various appliances. What are those? Those are electrical heating appliances. Where most of the energy is converted to heat energy. So appliances like fan, etc., all energy is not getting converted to heat energy, and which we do not want also. And in most of the electrical heating appliances, energy gets converted into most of the energy gets converted into heat energy, which is utilized. And we will discuss some practical applications of that. There is one important disadvantage. What is it? Because of getting converted into heat energy, it increases the temperature of the components of the electrical circuit, and therefore it changes their properties. So this is a major disadvantage of the heating effect of electric current. Now let us see practical applications of heating effect of electric current. I will be discussing 3 of them. So number 1, electrical heating appliances. Now, what do I mean by electrical heating appliances? We know most of the heating appliances like electric iron, kettle, toaster, electric oven, room heater, water heater, for example, immersion coil or geyser. So, all these are different heating appliances that we often use in our homes. Now, what will happen? Large amount of heat is produced in these appliances because they will have heating coils. They will have heating coils which are made of and which become red hot and which produce temperatures up to 900 degrees centigrade. And the coil becomes red hot and heat is generated, and that heat is used, for example, in electric iron. That heat produced is used to iron the clothes. Then the next one is electric bulbs. Now you know where these bulbs are used to produce light. So to produce light. So the electric heating effect of current in this application is used to produce light. Here it is used to produce heat. So if you look at some filament bulbs, we usually use a tungsten filament. Why we use a tungsten filament is because it has a very high melting point of 3380 degrees centigrade. So the electric heating is used to produce light. That means a very thin, high resistance tungsten filament is used, which has very high melting point, and when it becomes white hot, it becomes white hot and produces light. Without melting. That is why we use a tungsten filament which has a very high melting point. But then there is a disadvantage. Do you know that in present days we are not using these filament bulbs? The reason being they are not power efficient. They are not power efficient. What do we mean by that? Most of the electrical energy is consumed by these filament bulbs, and the bulb becomes heated up. Bulb becomes very hot, and only small amount of the electric power is utilized to convert into light. Therefore, the filament bulbs are not power efficient. So we usually use LEDs or tube lights, and most often we use LED lights these days which have no filaments. Now the next application is electric fuse. Now it is like this. It is like this. This is a fuse. Now what is this fuse? It is a thin, short, tin plated copper wire which has low melting point and of course high resistance. Which has low melting point and high resistance. What it does? In our domestic electric circuits, that household electric circuits, we use these electric fuses. What for? To prevent fire and damage of the electric appliances. Thereby, having this fuse will protect our appliances from damage. How does that do? When a current is increasing, then the fuse wire gets heated up too much because it has low melting point. It gets heated up and the temperature increases and it melts. Because of its low melting point, it melts and breaks the circuit, due to which current stops flowing. The moment the circuit breaks, current stops flowing. So that prevents the fire in the house due to overheating of the wire, or also prevents damage to various electric appliances like fridge, AC, TV, oven, etc. due to excessive current flowing through them. So a fuse essentially protects individual appliances by stopping the flow of any unduly highly electric current. These are generally rated as 1 ampere, 2 ampere. So depending on our requirement, we usually use different ratings. For example, if an electric iron consumes 1 kilowatt power when operated at 220 volts, 1 kilowatt means 1000 watts. A current of 1000 by 220 is required, so which is approximately 4.54 amperes will flow. Therefore, we prefer a 5 ampere fuse in this situation. Basically, it is undesirable to convert useful electrical energy into heat. In electric circuits, this heating can increase the temperature of the components and change their properties, that I already mentioned as a major disadvantage of this electric heating effect. So these are various applications. In the next video, we will discuss what is this electric power. Until then, keep watching, keep learning. Thank you.